All right, welcome everyone to another week of GROOT. Today we'll be hearing from Jackson Morris on symplectic orientations.
Thanks. Thanks for the invitation to do this. This is really fun. I mentioned this to Noah earlier. It's really early where I am, so if I sound like I'm rambling, just interrupt me and say, "What did you mean by that?" And we can figure it all out. And if you have any questions, feel free to just ask them. It's kind of hard for me to see the screen at the moment. But yeah, so I'm going to be talking about symplectic orientations today. This is a topic in motivic homotopy theory. So I'm going to work up from the ground up. I'm going to talk about complex orientations in the category of spectra. If you're not familiar with spectra, spectra like just like a generalized space is a good thing to have in your brain. I'll introduce motivic homotopy theory and what's called GL orientations. I'll move on to symplectic orientations and these things called formal ternary laws. And then we'll dream a little bit together at the end and see what we can do with this stuff. Okay. So this is classical. If you want a reference, you can look in what's called the Green Book by Ravenel. But a multiplicative cohomology theory or a ring spectrum, E is called complex oriented if there's a class in the cohomology of CP infinity called a complex orientation, which restricts to a generator of the second cohomology of CP1. And you can see by a string of equivalences, well, CP1 is the same as S2, and then we can just say that, well, this is going to be the same as pi 0 v. So we're generating pi naught of our ring spectrum with this complex generator when we restrict down on cells. The idea is that complex orientable cohomology theories have a lot of really nice properties, and we're going to try to leverage those incrementally throughout this talk. The first thing that we get is using an Atiyah-Hirzebruch spectral sequence, which takes the cohomology of CP infinity with coefficients in E star of a point and converges to the E cohomology, oh darn, it went away, of CP infinity. Everything is even. So the spectral sequence just collapses and we get the value of the E cohomology on CP infinity is going to be a formal power series on this complex orientation that we get. And by the same argument, you'll get that on two copies of CP infinity, we get this twisted thing, where we have one tensor, the complex orientation, and the complex orientation tensor 1. So there's like a lot of freeness going on here in the cohomology for a complex orientation. And as some examples, there's a lot of spectra that are complex orientable. So I should have complex over here. So some examples of these spectra are HZ, the spectrum that represents ordinary cohomology, MU, which I'll talk about later, which is the complex cobordism spectrum, BP, which is like the pth part of MU, KU, which is complex topological K-theory, KN, which is Moravec K-theory. If these names start meaning anything to you, it doesn't matter. The idea is that there are a lot of complex orientable spectra, and we can do a lot with them. But notable examples are MSP. This is the Thom spectrum for symplectic bundles. We'll get to that later. It's in the title of the talk. And more familiar that is not complex oriented is KO, real K-theory. Okay. And so we can talk about some geometry that we get from complex orientable cohomology theories. One of the things here is that complex-oriented cohomology theories have a theory of Chern classes. The CP infinity seems a little obtuse at first, but it's the classifying space of U1. It's where the line bundles live. So the choice of a complex orientation serves as a first Chern class for line bundles. And you can go on further with some, spectral sequence arguments or what have you to get the following. If we evaluate this cohomology theory on the classifying space for UN, where the n-plane bundles live, then it looks like this. And these, generators, these CIs are your Chern classes, where if you have a bundle, you just pull these back and they give you your Chern classes for your bundle. So we have a lot of really nice cohomological statements that we can make here. And another, idea of this thing, and this is equivalent, is if I have any complex vector bundle of rank n, then complex-oriented cohomology theories have Thom classes. So we can witness a Thom isomorphism with these guys. So if I have some complex rank n vector bundle, then I always get a Thom class, right? This is a map from the Thom space of my bundle. The Thom space of bundle being take the disk bundle inside of here, put a metric on each fiber, then the sphere bundle inside of there, and then we just quotient. Or you could try to think of 1-point compactifying all of the fibers. But the idea is that this Thom class gives this isomorphism that I've written down here. I take the Thom space or Thom spectrum of the bundle, and I take this over to Thom spectrum smash with X with a disjoint base point just along the diagonal map. I use my map U here. That's a map from the Thom space to E. And then I use the fact that E is a ring spectrum and I multiply. And this should be an isomorphism. And for complex-oriented cohomology theories, it is. So we have a lot of nice power here in understanding the cohomology of the Thom spectrum in terms of the cohomology of the base. Okay. But we can also go into algebra. And this is the point of view that I really want to try to leverage here. So this space BU1 or CP infinity, left you in suspense while I got a drink of coffee, has a lot of nice properties. One of the things that we're going to talk about is that it's an H space. It has some type of product structure. It's looser than in a group structure, but still gives us some way to multiply elements. And this H space structure, this map from CP infinity across CP infinity to itself, it represents the tensor product of two complex line bundles. CP infinity classifies line bundles, like I said earlier. And moreover, when I apply E cohomology to this thing, I get the following map. I take my complex orientation and it gets sent to one tensor XE to plus XE tensor 1, plus a whole bunch of sums of combinations of these things with some coefficients in front, right? Remembering that if I'm in cohomology, it goes now from CP infinity to CP infinity cross CP infinity, and we have formulas for what the cohomology rings of these things look like. But this is more than just a function. This gives a formal group law. This is a formal power series in two variables. So this was the one tensor XE and XE tensor 1 that I had earlier. And it satisfies some properties that I don't want to necessarily get into, but this is a well-studied thing. So we get a formal group law for every complex-oriented cohomology theory. And on the way that we've constructed it, this formal group law satisfies the condition that if I look at the Chern class for the first Chern class, or the top Chern class, for two line bundles, and I plug these into the formal group law, this is going to recover the Chern class of the tensor product of the line bundles. So this formal group law that I've made is exactly capturing some of the geometry of the characteristic classes for all my complex-oriented cohomology theories. It's a really cool hand-in-hand thing that we can do here. I guess I should also say is that I mentioned MU, the complex cobordism spectrum. This is the Thom spectrum associated to the universal bundles, EUN over BUN, the universal n-plane bundles. And as such, this is going to have the universal formal group law. In the sense that mu star is equal to this L. This is called the Lazard ring. And it's the initial object in the category of formal group laws. If I have a formal group law, I have a universal formal group law over L such that I can always map L to my other ring, and I can map the formal group law up here to the formal group law over my other ring. And so this gives us the following way to think about this, is that formal group laws over E star, these are just the same as ring spectra maps from MU into E. So not only can I talk about the formal group laws, but all of the formal group laws I can get are exactly in bijection with multiplicative maps from MU into E. Okay. And so I kind of gabbed a bit. So what? What's the point, right? And the point is that I could do more than just like, slap some geometry facts on the screen and more than just slap some algebra facts on the screen. This can help us understand the category of spectra structurally. These are really, really important classes of spectra that have been historically proven to like be enlightening. So the first of these that I have up here is the nilpotence theorem by Devin F. Hopkins and Smith, or Hopkins and Smith from sometime in the 80s or the 90s, depending on which reference you look at. And the idea is that if I have a ring spectrum, any ring spectrum, I have a Hurewicz map coming from the unit on this ring spectrum, and the kernel of this Hurewicz map from pi star r to mu star r consists of nilpotent elements. So if I want to check that a map between spaces is nilpotent, I only have to check this in MU homology. MU detects nilpotence. This is really powerful. The sphere detects nilpotence, but the sphere homology, homotopy groups, are hard to compute. This lets us like take our like nilpotence detecting device and shift it along to something that's easier to detect nilpotence with. This is what MU homology is doing here. And the other one that I think is important for right now is the thick subcategory theorem. So the thick subcategory theorem says that thick subcategories of spectra, if I work at a prime P, are precisely generated by these things called type N spectra. Spectra's type N if it has this, property involving Moravec K theory that seems appropriate. And the idea is that this Moravec K theory is the unique complex-oriented spectrum that has a formal group law having height exactly n at a prime p. I'm implicitly doing now. And the thick subcategory theorem is saying that the heights of formal group laws classify the thick subcategories of the category of spectra at a prime p. And if you're unfamiliar with thick subcategories, it's kind of a way to think of the whole category of spectra as a ring. And the thick subcategories are like the prime ideals of this ring. So we're detecting kind of the spec of this category. This is why it's called the Balmer spectrum, is what some people use. So complex-oriented spectra, super useful for geometry, for algebra, getting some formal group laws in there, and for understanding some of the structural properties of the categories of spectra. This birthed a field, the proof of these theorems, the nilpotence and thick subcategory theorem, that really started to use all of these ideas together, birthed a field called chromatic homotopy theory. This height filtration on the category of spectra leads to the study of this thing leads to like many, many nice understandings and a deeper familiarity with the category of spectra that has been very, fruitful over the last 40 years. So the immediate question is, can we do this in motivic homotopy theory? So I'm going to talk a little bit about motivic homotopy theory and try to answer that question. So motivic homotopy theory goes by the slogan of it's a homotopy theory for smooth schemes. So I previously was working with spaces and then I upgraded to spectra. But what if I just wanted to work with schemes, a type of space that inherently has some type of algebraic data on it? And we can do this. Blavatsky, Levine-Morel et al. Did this in the late 90s, early 2000s, and has proven very fruitful. So let's go into the construction of some of these categories. So we're going to start with our smooth schemes over some field K, and we can embed this by the Yoneda embedding into these simplicial presheaves that's on here. It's a bit of fancy words we don't need to get into. We should think of the pre-sheaf category as adding all the co-limits that don't exist in the category of smooth schemes over K. It's called the free co-completion of our category. And this simplicial description, this little s right here, just lets us do a little bit more homotopy theory. A good way to think about this is the pre-sheafs on my smooth schemes aren't sets anymore, but they're types of spaces. Then we have these functors L, A1, and L nis. This A1 just makes the affine line contractible. Just like in homotopy, we want R to be contractible. And this nis is a descent condition that's similar to like Meyer via torus. It's nothing too important. It's a little technical.
Jackson, is this simplicial pre-sheaves like an infinity category thing, or is it like just one categories?
It does work infinity category. Yeah, it's an infinity category thing. Yeah, and I guess you could equivalently think of simplicial objects in the pre-sheaf category or pre-sheaves of simplicial sets. Currying isomorphism gives you that they're the same. Thank you. So once we do this process, we land in this SPC over K, which I'm going to call motivic spaces. It's like our unstable motivic homotopy category. We've done a couple of procedures to get here, so we should identify some objects that we want to work with. But we started with the Yoneda embedding, and we can just embed all of our smooth schemes all the way through this category. So the unstable homotopy category we've constructed really does possess all of the smooth schemes that we started with, and we can talk about doing homotopy theory with them. So any smooth scheme over K is inside of here. In another sense, I say the constant simplicial direction, you can think constant space direction. And when I say simplicial set, you should think space. All of my spaces are inside of this category. So this category is like gigantic. It's so big. It's amazing. We have so many spaces in here to work with. And now we can try to do some homotopy theory. And as a bit of motivation for like what seems like an obtuse definition, I saw this recently and I thought it was really cool and I wanted to put this in here. If we do this without the notion of like smooth schemes at all, if we take the category of pre-sheaves on smooth manifolds, which satisfy a Meyer via torus condition, again, this Meyer via torus should be similar to this Nisnevich localization, and sends projections to equivalences, that should be similar to this condition. The category that we end up with actually is the familiar category of spaces. It's like a funky way to build up this category. It's really interesting. So this motivates the definition, I think, in my brain. And I should also say that since we're landing in spaces or simplicial sets, we inherit a smash product. And a really important structural fact for the motivic homotopy category is that if I take the constant S1 in the space direction and I take the geometric circle that comes from the punctured affine line and I smash them together, then in this A1 homotopy category, this is equivalent to the projective line, to P1. We can see this in the following way. We have the usual push-out square. We have the double cover of P1 by A1 pointed at 0 and by A1 pointed at infinity. And the intersection of these things is a punctured A1. This is a pullback square by construction. But in this homotopy category, A1's contractible. So the corners, the top right and the bottom left corner of this diagram just go down to a point. And this P1 ends up being just a simplicial suspension of GM, which is exactly what I'd written on the other slide. But this leads to a notion of not one type of sphere, but two types of spheres in this category. So everything that we do is bigraded. We have bigraded spheres. We want to look at the copies of the simplicial direction and the geometric direction. We can look at bigraded suspensions, bigraded homotopy groups. I probably didn't write it here, but all of my homology and cohomology theories are also going to be bigraded. Everything's bigraded. And the grading convention that I'm going to use is that the P here is the total degree, and the Q here is the geometric degree, which is what these things are supposed to indicate. Okay. So we have this category spaces. I want to work with spectra. And we can stabilize this category by classically, we invert smashing with the circle. Here we have two types of circles. If we invert smashing with this combination of both circles, then we stabilize with respect to both of them. And we get a category of motivic spectra, this SHK here. So the objects here are motivic spectra, and we should talk about some examples. So again, motivic spaces. I can start all the way back in schemes, even if I wanted to, push those schemes all the way to motivic spaces. And there's a left adjoint from spaces to spectra that is the suspension spectrum functor. It takes a motivic space to its suspension spectrum. Just keeps it inside of there. And the homology or the cohomology of this spectrum is going to recover the homology or cohomology of the underlying motivic space, just as classically. We have a sphere spectrum, which is going to be the monoidal unit for the smash product that we have in our category, the suspension spectrum of the zero sphere. We have Eilenberg-MacLane spectra, which give us motivic cohomology with A coefficients, where A is some abelian group or ring or whatever you want it to be in the entire world. And we also have some more, some different spectra. I don't have another descriptor, I guess. We have this MGL, which is going to play an important role here, what's called the algebraic cobordism spectrum. We have an algebraic K-theory spectrum, KGO, and we have a Hermitian K-theory spectrum, which I'm going to denote by KQ. In the literature, people use a lot of different symbols. Sometimes they use KO, sometimes they use GW, but I like Q. Oh. And the definitions of these things are not too important. The important thing is the analogy with classical homotopy theory. So these are all respective, but MGL and KGL and KQ are to this motivic category as MU, KU, and KO are to SP. Any of the statements you want to make about these things in the classical category, if you wiggle them around enough, you can make the same statement in the category of motivic spectra. A really clear case is this bottom line that I've written here. If you look at the two p homotopy groups of MGL, then you get the pth homotopy group of MU. And this should give us an inclination of what's coming, because we saw that the homotopy groups of MU were the Lazard ring, and this was the holder of the universal formal group law. So living on the 2n line of MGL is the Lazard ring. So we should be able to imbue this situation with formal group laws, and we're going to be able to. So we're going to introduce a notion of orientation now that was done by Levine and Morel in the mid-2000s when they made a really precise construction of algebraic cobordism. So we say that a motivic ring spectrum is GL-oriented if there's a class in E21 of P infinity, which is E21 of BGL1, just as CP infinity was BU1, which restricts to a generator in just the analogous statement that I'd had before. I want to take some class in cohomology of the object classifying line bundles with a particular structure, and I want this to restrict down to a generator of the zeroth homotopy group. Okay. And this MGL is going to be the holder of the universal such orientation. And I'm not going to go into the details of the construction of this thing, but it's a motivic Thom spectrum. We take the Grassmannian's BGLN, we take the universal n-plane bundle over these things, we glue together the Thom spaces of these bundles together nicely, and we get this Thom spectrum MGL. And the idea here, in analogy with the geometry from before, is that we have Thom classes now for algebraic vector bundles. If I have a rank n algebraic vector bundle V over X, where X is now some smooth, I should have had K scheme, not S, sorry. SMK. Then it might be a little hard to make the Thom space, but in the category of motivic spaces, we're completely fine. We can make this quotient and everything is all good. And if I have a GL-oriented spectrum, then I have a Thom class in the 2n, n cohomology of this Thom space, which gives the Thom isomorphism that I want. I'm probably missing a tilde over one of those e's, but you can fill in one of them if you want to. The idea is that we have a Thom isomorphism, and we can recover some of the cohomological facts that we'd had before. And in our, analogy that we'd had before, HZ representing motivic cohomology, MGL representing algebraic cobordism, and KGL representing algebraic K-theory are going to be GL-oriented. And this KQ, our KO avatar here, is not, just as KO was not complex-oriented. Okay. So we should look at what we get here. Just as in before, we have an H space structure on P infinity. This is actually, I think, an abelian group object in the category of in K schemes. That's stronger than that, but we don't need it. But pulling back along the H space structure map, just as in before, we get a usual formula. And the image of the GL orientation under this map gives us another formal group law. So if we have a GL-oriented spectrum, I get a formal group law over it, just as before. And I get a similar statement for Chern classes. The cohomology of the Grassmannians is going to give us the universal Chern classes. This formal group law is going to characterize the formula for the tensor product of algebraic line bundles now. So a lot of the same story still holds. If I look just at the geometry, or even just at the algebra, I have a way to associate to a GL-oriented spectrum a formal group law. I wouldn't be giving this talk with another thing that I want to talk about if this solved every problem. So, oh, sorry. We get the same formal group laws for HZ and KGL as we had before. This is a slide that I'd forgotten. I should write, this is the same as HZ in spectra. This is the same. And when I say same, I mean same formal group law as KU. Not very important, just a technical point. The problem that I was alluding to was that MGL doesn't detect nilpotence in the motivic homotopy category. There's a map called the algebraic Hopf map, which looks like taking points in P1 to their coordinates. And this map is not nilpotent in the stable stems, but MGL tensor with eta is 0. In fact, if I have any complex or sorry, any GL-oriented spectrum, then when I tensor with the Hopf map, I get 0. It's actually an if and only if. It's a way of detection. Another thing that's weird about motivic homotopy is that this is a positively graded element that's not nilpotent. So we already, our Nishida's theorem is false. So very interesting. And another thing that this eta gives us, for example, is that there are more thick subcategories in the stable homotopy category. So things are a lot more complicated here. The same story that we had in these really rich structural results can't hold here. So we want to alleviate this. We want to know those answers. So what can we do about this? I'm going to get more coffee really quickly. Okay, I'm back. So we want to talk about some of these categorical things that we can do now. Enter symplectic orientations. So we're just going to introduce a new type of orientation. we're going to say that a motivic ring spectrum is symplectically oriented or SP oriented. Sorry, this SP doesn't mean the category of spectra. If there's a class in H42 of HP infinity, so quaternionic projective space, which is BSP2, which restricts to a generator, again, of pi 0, 0 of E. But the idea is that HP1, the object which should be classifying symplectic line bundles, this is S42. We're just bumping up the dimension a little bit higher here. And remember that a symplectic vector bundle is one which I have a symplectic form on all of the fibers, which is some non-degenerate anti-symmetric bilinear form. Say maybe omega goes from V, tensor V to V. So all of my vector bundles are equipped with a form like this. And I think as I write later, equivalently, this is a choice of Thom classes for these bundles, right? I want to have a Thom class for these bundles because this is exactly what an orientation should be giving me. And the existence of some type of symplectic form automatically implies that symplectic bundles all have even rank. So when I say symplectic line bundle, I actually mean something that has rank 2. It's not rank 1. Again, I have a Thom spectrum, which should be classifying these things. MSP, symplectic cobordism is another way to think about this. And it's built out of the Thom spaces of the canonical symplectic bundles over the classifying spaces of SP2N. And something that can make this a little less obtuse is that I have a map of algebraic groups, SP to SL to GL, and I can pull back along this map, meaning that if I have any GL-oriented spectrum, I automatically get an SP orientation on this guy. So we've expanded our class of orientable objects with respect to this new orientation. And this is the best thing ever because I love KQ. KQ's oriented now. This is baller. We can play some games with my best friend. This is so fun. Let's think about this. If we're in analogy with before, we want to go into some geometry. We talked about characteristic classes. We have them here. There's a symplectic Thom isomorphism, which gives us these things called Borel classes. And the Borel classes play the role of Chern classes in complex or GL-oriented spectra. The idea is that they come from the cohomology rings of the classifying spaces again. If I take BSP2N, then I should get form a power series on the nth B1 up to Bn Borel classes, the universal such that pull back. But now we enter a new type of problem. So first problem is that if I have two symplectic bundles, their tensor product is not symplectic anymore. So moving away from geometry and into algebra, one of the nice things that I was kind of implicitly using was that if I take two complex or GL-oriented line bundles and I tensor them together, I get another complex or GL-oriented line bundle. And this is not true here. A symplectic form, if you tensor with another symplectic form, is symmetric. It's not alternating anymore. So we have a bit of a problem here. And there's a kind of silly fix to this that Ivan Panin found in the early 2010s, which is that if you take three symplectic bundles, well, their tensor product is symplectic. It goes back to being the alternating thing that we want it to be. So we can try to use that fact to model how we want some type of formal object that understands the tensor product of line bundles to work. So take now, instead of two copies, three copies of HP infinity. We know that if I look at the cohomology of this thing, here E is going to be SP oriented. It's going to be a power series on three different classes, which are going to represent the Borel class of the canonical symplectic bundle over each of these HP infinities respectively. This as what I've written here. X is B1 of U1, Y is B1 of U2, that should say Z is B1 of U3 for the canonical bundles over these guys. And we want to find some formal operation that when I spit in these Borel classes, I should get out the Borel class of the tensor product of the bundles. This was the thing that motivated what we had done before. But now we hit problem 2. Right? These are rank 2 bundles. If I tensor 3 of them together, it's a rank 8 bundle. I was nicely using the fact that if I have line bundles and I tensor them together, I get another line bundle. I don't get a line bundle here anymore. I get something bigger. I have 4 Borel classes for this triple product that I need to consider now. Well, the solution is just deal with it, right? We have 4 Borel classes. Let's just consider them. So there's an abstract notion of a formal ternary law that I'm not going to write up here that is much more complicated than a formal group law. But I'm just going to say out loud that if I have some symplectically oriented ring spectrum, it gets 4 ternary laws that do satisfy the properties that we want. It's some power series in 4 variables, and it does end up recovering the Borel class of U1 tensor U2 tensor U3. I get one for each of the Borel classes for this bundle. And I also have a total where I just add up the Borel classes and I tack on some dummy variable t. And this is our analog of a formal group here. And they do satisfy the desired equality. I'm not going to prove this, but this is what we wanted. If I take the Borel classes of these symplectic bundles and I look at the Elf formal ternary law with those as the inputs, it's the same as the Elf Borel class of the triple product. It recovers something that we wanted and that we saw in formal group laws. And just as before, there was an initial object in the category of formal group laws called the Lazard ring. And in the category of formal ternary laws, there is also an initial object. So I map any formal ternary law over a ring to one over the other via a map from what's called the Walter ring to whatever my ring spectrum is. So the homotopy groups of the symplectically oriented spectrum. Also love the name Walter ring. That's pretty cool. Anyways, we got through the content. Now I want to dream a little bit and talk about some problems. We have this whole setup. We have these symplectically oriented spectra. We have a new class of spectra that encompasses our old class of spectra, which we can now orient with respect to some vector bundles that with some suitable structure on it that have some algebraic group determining the structure here. Seems like everything should be doable. I even have some attachment to some formal abstract algebraic nonsense, but there are problems. And I should say that these are problems that should be able to be overcome. This is a very new and rich story. I think the first paper on a Borel character came out in 2019 or something. This is very new. So the problem is that things are complicated and they don't get any better. Formal ternary laws are very hard to compute. Given an just if you hand me a symplectically oriented spectrum, it's really hard to determine what the formal ternary laws of this thing are. There's a way to try to compute this using Buchstaber's what are called 2 groups, but it's unclear how to do them in general. We've determined them for the pullbacks of GL-oriented spectra to SP-oriented spectra, and we've determined the formal ternary laws for Hermitian K-theory, KQ, which makes me happy. But there's a lot of other questions that are still open here. Formal group laws come about as kind of the, if you take an algebraic group or a Lie group and you look at the identity and you take some formal neighborhood and you represent the multiplication in terms of power series, this gives you a formal group law. But it's unclear what type of situation a formal ternary law arises from other than this ad hoc construction that we've done. So if one could find an object where these come from, it would be a lot, more motivating and maybe more clear how to work with these things. given that they're more complicated, if I work at a prime, we don't have an analog of height. The height was really important when we worked at the Balmer spectrum. Classically, it gave us the stratification. We don't really know how to stratify the motivic Balmer spectrum here because we don't have a well-defined notion of height yet. On a more homotopical level, we don't have a Landweber exact functor theorem, which is really important when we're looking at complex-oriented spectra. It's one of the keystones. One of the problems with finding a Landweber exact functor theorem is we don't really know what the Walter ring looks like. If you look at when Quillen showed that Mu is the Lazard ring, right? This was a proved isomorphism, right? He had to construct the Lazard ring in a kind of fancy way and prove this isomorphism from Mu star to the Lazard ring. You define the Lazard ring akin to how you define the Walter ring. It's the initial object, so you just quotient out by everything you can. That doesn't give us a nice description of the ring, and we don't really have a nicer way to think about it at the moment. And the hardest thing is that we don't know the homotopy groups of the universal Thom spectrum. Even classically, we don't know the homotopy groups of MSP. What we know is that they're messed up and have a lot of torsion. Mu is a polynomial ring on even degree generators. MGL has Mu star hidden inside of it on the 2n line. We have no idea for MSP. It's really tricky. But in lieu of these problems, which I think are solvable, we can dream a little bit. So bear with me. Everything works out. And I really do believe that everything works out here. One, there should be a way to compute formal ternary laws by computer more efficiently. I was talking to one of the people that is researching this recently, and I was like, why are you computing it this way? And he just went, I don't know. And so there should be a better way to do this. The only answer to these questions on why we compute this way is I don't know. There should be some type of stackier, more formal language to give where formal ternary laws are coming from. One of the problems is that it's possible that we don't get a stack a priori that the formal ternary laws come from. It's something called like a two-stack, I think. Don't need to get into this conversation. No, I think you're at the table when we were talking about this, but there should be some type of universal way to parameterize what's happening here. And this should talk about the Balmer spectrum here. This should give us clear descriptions of some primes, maybe all primes in the Balmer spectrum. Personally, I believe that all of the primes in the Balmer spectrum come out of the theory of symplectic orientations because motivic homotopy theory is a bit of a quadratic enrichment of classical homotopy theory, given that the endomorphism of the sphere is the ring of quadratic forms, the Grothendieck-Witt ring. I think that if you look at these quadratic bundles, you should be able to unlock the structural facts going on here. And there should be some bi-graded notion of height going on. And MSP should be able to detect motivic nilpotence. Pretty confident that it detects eta. So if it detects this algebraic Hopf map, I think it will detect everything else. I think I have one more thing to say. And this is that there should be an isomorphism from the Walter ring to the homotopy groups, at least on the 2n line of MSP. This is what we know, given that we have a map out of the Walter ring to anything and out of MSP to anything based on how they are constructed. So this map should agree, and we should get an isomorphism between the universal formal ternary law holder and the universal symplectically oriented spectrum. I think that's all I have. So this is a fun thing, and thanks for listening.
Let's thank Jackson for a wonderful talk. All right. Does anyone have any questions?
I have, I guess, a comment and a question.
Yeah.
Surely you've seen like this PhD thesis of this person that like gives some partial results on the Balmer spectrum in the motivic setting.
Yes.
Okay. And well, so I wonder how maybe that plays with formal ternary laws.
So personally, I don't know. So when I've talked to the people that are thinking about formal ternary laws, they tend to be more geometrically minded. And the question of how do formal ternary laws give us information about the Balmer spectrum motivically hasn't really been asked. I think the dream is out there, and like I've talked to people about the dream, but no one has written up anything, and I don't think people are thinking about it. I would imagine that these, I think I know the paper you're talking about. I think I was looking at it a couple of days ago. I'm pretty sure that a lot of these things come about via formal ternary laws. I don't know how to prove it, but I would like to think about it.
It seems interesting. And then I guess that was my comment that turned into a question. And then my question is that in equivariant homotopy theory, we have like a pretty good picture of how equivariant formal group laws go. When you Betty realize, I guess, there's a way to Betty realize and get C2 equivariant stable homotopy category. So is there some way to maybe relate formal ternary laws under Betty realization with C2 equivariant formal group laws, perhaps?
That's possible. It's also possible that the formal group laws that do exist via the GL orientations are the ones that Betty realized to the C2 equivariant formal group laws. I think that would be more plausible. I also know that there's a computation of like the Balmer spectrum in like G equivariant homotopy theory. I don't know how this would interact with formal ternary laws. Another thing I should add is that formal ternary laws, or maybe I shouldn't say this, symplectic orientations, and again, the following theory of formal ternary laws, are not unique to motivic homotopy theory. Classically, these are the Pontryagin classes. And like one can define this geometrically completely fine, and some people do think about this. It's just that the stackier side of things hasn't been developed because there was no need for it because complex orientations rule. But like a priori, one could do this C2 equivariantly and think about what the story gets, and maybe the C2 equivariant stuff, formal ternary laws. And I would imagine that this would be the same story as like our motivic formal ternary laws. Did that answer your question?
Yeah, thanks a bunch.
Cool.
Great. Yeah, any other questions? All right, so stop the recording.